Okay.
All right, thanks.
So
So yeah, go ahead.
yeah, so it's my pleasure to introduce Dr. Maria Chan, who's at the Center for Nanoscale Materials at Argonne National Labs. And she and the team that she works with has been sort of a leader in using AI and ML techniques for the design of materials, and in particular, including semiconductor materials, which is the subject of this school. So Maria, take it away.
Great. Thank you so much for the introduction, and thank you, the organizer, for inviting me to give this talk. I apologize for not being able to be there in person due to many travels. But I am happy to chat with anyone who's interested. I'm gonna talk about the work, but the work is almost exclusively from the my postdoc students who are listed here, and I will try to bring up their name as we go on. In addition, I've had the fortune of working with a lot of experimental collaborators. That was always a great education for me, having been trained as a computational person to have these deep discussions and collaborations with people who use a variety of state-of-the-art characterization techniques, as well as also people who work on AI, ML, and data science in general. So I think Murat gave a great, I always enjoy hearing his talk about designing materials, figuring out what was stable and how to synthesize them. So I don't think we need to emphasize the point that atomic structure, how atoms are arranged, matter. I really enjoy taking, I have like these physical models of graphite and fullerene and diamond, and take them to schools. And this is one where I did a virtual visit to an elementary school. And it was really cute, how the kids are really amazed at like the same atom arranged different ways, kind of their very different properties. But of course, all of you don't need that particular point. But one thing that may not be emphasized as much is that it's not just structure, like crystal structure, as many of the work, including ICSD Materials Project, all of the GNOME and work that are really ongoing in materials and AI, those are concern themselves with periodic crystal structures. But there are additional complexity, and I think Murat brought that up. You have grain boundaries, you have interfaces between different materials. But more broadly, the problem of nanoscale structures or nanostructure actually do play a big role in many problems. Things like, explicitly nanostructures like nanoparticles, nanowires, but also things like surfaces and interfaces, grain boundaries. Those are all very critical in any kind of device performance, especially in electronics. And so that's something that we focus on as well. We look at how nanoscale structures drive properties, and we specifically also look at how we determine these nanoscale structures. So here are a few examples. Batteries is another one of our main focus. Photovoltaics, also catalysts. The background behind me is a complex synergistic catalyst made of platinum cobalt nanoparticle, as well as non-platinum group materials that are in a mixture, and they do different parts of the catalysis. So all of these nanoscale structures do play a big role. There are different aspects of the work we do. One of them is from structure to properties, so starting with structure and determining properties. So that's very much in line with what Murat has been talking about in terms of AI material design and prediction. Maybe I don't have to repeat this, but for 30 years or so, maybe from the mid-80s to mid-2000s, there was a huge boom in materials, computational materials, because computers are getting better and faster and bigger, but also because of the development in solving quantum mechanically equations regarding materials properties, primarily density functional theory. So I don't have to belabor that. But I was curious, how big is density functional theory? And so I did a Google Scholar search, and it gave 2 million results. Now, not all of that will be materials. There is nuclear density functional theory, but it's a much smaller field. So most of this will be chemistry materials. but how big is 2 million? Google Scholar results. I didn't have like a sense of scale. It's big, but how big is it? So then I didn't put the screenshot, but I did another search for X-ray diffraction. So X-ray diffraction is 100 years old, and it has 4 million. So in a sense, density functional theory was really an explosive influence on scholarly research. But as Murad had mentioned, it's slow. There's a lot of things it cannot do, both in terms of time and length scales. There are also, of course, other issues with it, which people are trying to fix. But so there's been a lot of effort on improving predictions, especially structural predictions and energetic predictions, which are tightly tied to structures, using these machine learning force fields or AI force fields. This two paper were mentioned in the last talk as well. But there was a different route, and maybe that's a slightly older route even, is to directly go from structure to property using DFT trained data. So instead of having a force field, so you don't get structure in this approach, but you get properties. We've a couple of years ago, my former postdoc, now a professor at Purdue, Argonne, wrote this sort of short primer. So for someone who's new to this area of materials design, computational data-driven materials design, this may be a good read. It was only 2 or 3 pages. One of the key things I like to emphasize is we mention a lot about the ML tools. We mention a lot about the computation, but really the hardest part, and I've done this a number of times, the hardest part is really figuring out where is your chemical space of design. What is your choice of structure and composition, and what is the information that limits your search? At this point in time, this part is still very much human. No matter how much we can automate the DFT calculations, the model training, the validation, the searching, and now we've seen results from the last talk of like great explosion in number of structures and materials that can be considered. But still, there's still a lot of like domain knowledge and chemical sense that can go into making a project like this successful. So I'll give you a small example of a design of perovskite halides. A lot of our group's work had been on photovoltaics, so perovskite halides was one of our interests as well. These are very low cost, very high efficiency relative to the cost of solar cell materials. But they are a weird beast. Unlike traditional semiconductors, they are made of inorganic and organic components. Unlike traditional semiconductors, they are very unstable. They are water soluble. They are sort of all kinds of porous in a sense, because these are very open structures. So there's a lot of sort of work that has gone on to it, solving a lot of the problems. One of the problem, but also opportunity for this type of materials is the fact that they are so compositionally flexible. This is a perovskite structure with 8-site and B-site cations and a halide ion, not fluorine, but all the other halides. The A-site cation can be a wide range of organic molecules as well as some inorganic ions. B-site cations can be a number of different main group ions, and I think people don't try transition metals, mostly because of the size. But the other additional flexibilities that they can be mixed. So the B-site can have mixed cations. So what we did was apply what we wrote in the primer, designing the chemical space, doing the high throughput calculation, determining the screening parameters, and then determining the candidates that come out. So the chemical space, as I mentioned, are these A-site and B-site cation, but in particular, we wanted to look at B-site alloying. So mixing different cations in the B-site. In addition to, I mean, in principle, of course, this is an infinite chemical space because any kind of mixtures are available. But we discretized the B-site to 1/8 just due to the size of the supercell. So if you enumerate all of them, that will be 18,000 compounds. But we wanted to push, sort of the envelope of what is, how aggressive you can be in terms of training data. So we did only 200 calculations. The calculations were done with both PBE and HSE, so semi-local functional and hybrid functionals, just to look at the difference. We calculate thermodynamic properties like decomposition energy, electronic properties like band gaps, as well as figure of merit, which tell us how the absorption spectrum of the material work with the solar spectrum. There are also things that are derived from the total energy, including the decomposition energy, because one of the problems of this type of materials is how stable is it? Does it phase segregate? So we will look at how what the energy of this material is relative to decomposing into binary compounds. This is a result of shallow neural network models that against DFT data. So on the vertical axis, all these parity plots, the vertical axis are machine learning predictions, and the horizontal axis are the DFT calculations. If the model is perfect, everything will fall in this black line. You can see that the models are actually quite reasonable, especially in energetic information, because DFT really is most valuable, most accurate when it comes to energetic information. So you would sort of expect the noise in the data to be less as well, and definitely the errors in the decomposition energies are very small. Lattice constants as well, it's fairly well predicted. Even things like band gap and optical absorption, which are electronic properties, you have, of course, an error in the PB band gap compared to experiment. But the mitigating factor in hybrid perovskites is that when you involve heavier elements, there's usually a spin orbit coupling interaction. And if you ignore spin orbit, you actually overestimate the band gap. So it's not like a recommended strategy to use error cancellation, but a lot of times it does turn out that way, that errors do cancel, and you get somewhat more reasonable predictions than you would expect otherwise. But we also have HSE band gap, just to give us a sanity check with those. But if we just stop there, use the training data, and then look at the results, we would know how the model will perform within the exact same space that we train on. But I often feel that that's not sufficient. We need to stretch our model a little bit. I know there's this mantra that AI ML is good for interpolation, not extrapolation. But I think it is important to do this stretch exercise in general. It's in a way trying to stress test your model a bit to see if you just change your space just a little bit. I'm not saying that to use a model trained on DFT data to predict cancer, right? That's not reasonable. But in our case, what we tried to do was look at different a slightly different chemical space. For example, A site mixing or halide site mixing. So instead of the B site cation mixing that was included, we mix the others. Those are the orange dots. And also neo B site cations, if we included a different B site cation, because we are using the atomic descriptors, the elemental descriptors. If we use the new B site cation, we will still have an input. We can still predict an output. And in some cases, this was the 3x3x3 supercell. That was just like a different computational approximation. Instead of a smaller supercell, we use a bigger one just to see if that makes any difference. So you can see that there is a slight sort of degradation in the performance, especially when you use a new B site cation. The decomposition energy becomes a little bit worse than before. The band gaps are still fairly reasonable. The errors was 0.2, and now it's about 0.25 or 0.34. So you can see that by stretching the model, there's slight degradation in performance, but it's still reasonable. And we need to keep doing this until it breaks. That way we can know what is the range of applicability of this type of models. As a result, we use the model to screen all these properties, starting with stability, if the material is stable and not decomposing. And then we look at the band gaps. What are the band gaps that are reasonable for photovoltaics? And then the next step was defect tolerance. That's very important. What makes perovskite halides, this gold standard in electronic materials, is this really long lifetime, low recombination, and all that has to do with like having benign defects. And then we have screen candidates. So in the end, we got a few 300 or so candidates. There was a mix in composition of the A and B and X site. But along the process, we learned something about this chemical class of materials. When we screen by stability, we realized that all the potassium was eliminated. So potassium is too small as the A site cations. There have been rules that were developed called Goldsmith tolerance factors that would tell you that. But it comes out of the model basically, as a data-driven approach. So it's kind of like, you sort of know from experience that, smoking causes cancer, but having this like demographic data that shows you, it's very interesting. Another a step looking at band gap, it would show you that the lead, tin, and germanium are preferred B-side cation. They have the better band gap. That it may also not be completely surprising. But then what's really interesting is that when we look at the defect tolerance, all the chlorides were eliminated. There had been talks in the very beginning of the field, this explosion of perovskite halides, that chloride does something really useful. But ever since, there's been a lot of debates, like what does the chloride actually do? But it seems from this data-driven approach that shows you that the chlorides are really spelling trouble for defects. As well, all the potassium was eliminated and very few cesium rubidium are left. So that gives you the reason that the organic A sites were much more successful. By trial and error, people do experiments and they find the ones that perform better are the organics. But what this points to is that it's the defect tolerance that makes the inorganics A sites much worse. So this exercise is dual purpose. Like we would like to find perovskite compositions that are interesting and useful, but also we'd like to understand, when you have a very broad chemical space, what are the combinations that work and why do they work? So this is how AI ML can give you not just like materials, but also some understanding. So moving forward, I just switch these orders a bit because I want to go from bulk material to defects. So as I mentioned earlier, defects are what drive a lot of semiconductor properties. And we have been, as a computational materials field, we have been working on defects for a couple decades as well. Many of the work was developed by previous researchers, particularly Van der Waal in UC Santa Barbara. There was a lot of development on using density functional theory to calculate defect properties. The way you do this is you start by making a big supercell. I mentioned defect earlier and supercell size, and this is why. We want to calculate the property of an isolated defect. However, DFT is always done periodically for materials. That means that in your simulation cell, the box is repeated in every direction infinitely. So you have an infinite array of defects instead of a single isolated defect. But you want to make the defect a little bit far away from the periodic image so that you don't have too much of an interaction. So that's why you need a big box. When you calculate the defect total energy, you can also derive this type of defect formation energy diagrams. It shows you the energy to make a defect as a function of Fermi level. In a semiconductor, the Fermi level, of course, ranges from the valence band maximum to the conduction band minimum. The positively charged defects have positive slope, and their formation energy increases as you move your Fermi level from the VBM to CBM. And opposite for the negative defects. If you have a neutral defect, it would be flat here. And positive and negative charge defects can have different charge states. They can have 1 or 2 plus or 1 or 2 minus. Usually, occasionally, you will see something like 3 plus or 3 minus. When the lowest energy defect changes charge state from a +2 to a +1, for example, or -1 to a -2, that's where a defect level occurs. That's a charge transition level. And those are the levels that will often cause a recombination of carriers. So this whole machinery is there, and the problem is that this takes quite a lot of computer power to do, because you have to set up a supercell, and DFT calculation scale as, n to the power 2 point something. So the bigger the cell, the more expensive, but also not linearly more expensive. So what we try to do is to use machine learning, same idea, have the input from the structure and elemental properties, train a model on DFT data, calculate it, and then try to determine the property directly using this trained model. Here are the input descriptors. There's the AB, which is the semiconductor, M, which is the impurity, and we can have elemental properties of A, B, and M. So these are things like electronegativity, ionic radii, all those other properties of the element itself. We also look at the defect coordination environment, what atoms are surrounding it, how far, and so on. And we, in addition, use these so-called unit cell calculations. Instead of having a supercell, we stick the defect in a unit cell, much smaller DFT calculation. And even though we don't rely on that as an isolated defect, it actually gives useful information. So this is a choice we often have to make when it comes to building training data and models. All these other properties are cheap. You can evaluate elemental properties in a microsecond. But a DFT calculation, even if small DFT calculations, it's a lot more expensive. It could be a few minutes, or even, well, okay, a few minutes, I think, for these unit cell calculations. So whether you invest, a microsecond or 100 microseconds or a few minutes makes a big difference. But if you are limited by accuracy, then maybe those few minutes or something you can still afford, for your training data, that might still be something that's worthwhile. So one of the things we do is look at the output, which is the properties of interest, in this case, defect formation energies and charge transition levels, and how they correlate with the different inputs directly. So this shows the correlation coefficients. Light colors are no correlation, dark colors are a strong correlation. And you can see that the unit cell defect calculations have much stronger correlation to the outputs. And some of the others also have, somewhat moderate correlation. But of course, that alone, is not sufficient. You're not going to use a linear correlation to actually get your answer. So we train different models. We started with some random forest models this is the cadmium chalcogenide systems. And that's another thing we have to figure out is how big does your training size need to be, and what are the input properties that give you the best outcomes. So if we only use elemental properties, you can see the green here. It still gives you something reasonable, but if you did include the unit cell defect properties, it's much better. So the blue here is including both of those. This is for formation energies. However, for defect levels, the unit cell defect properties does make an improvement, but a little smaller improvement. And these training curves show you how your errors decrease as a function of training set size. So you can sort of choose. Ideally they saturate, but you can often see that it will keep going smaller and smaller. So it's more or less a choice of how big the data set you choose and then stop. And these are very small data sets compared to the numbers that you saw from Murad's talk before. So here are some results. Again, some parity plots, machine learning prediction versus DFT calculations for formation energies. and for defect levels. Some of the things to point out is that in some ML models, you can actually output an uncertainty. And that's very helpful. That tells you, how sure you are of your answer, and we should use that information. The other thing is also this idea of stretching. So in this particular project, we use cadmium chalcogenide, single chalcogenide, so sulfide, selenide, and telluride as a computation and training and test data. But then we then did some calculation where we mixed the anions, telluride, selenide, and so on, just to see how well the model performs. You can see that there's a slight degradation, but in this case, quite slight in the performance if you go slightly out of sample. So I think this is a useful exercise. And then how is this useful? Once we get the machine learning model. So one of the things we could do is to use it to screen dopants. For semiconductors, you need dopants to introduce carriers often, especially in the case of cadmium telluride, which was the origin of this story. Intrinsically has very low carrier mobility, so we need to carrier density. So we need to introduce dopants to it. And with this ML model, we can put in any dopant we want, oxygen, fluorine, arsenic, any kind of dopants, and then calculate whether they have a deep level, which would be detrimental, and whether they have low formation energy, which would make them dopable. So all this allows us to evaluate, different dopants for new materials and compositions. We did a little bit of literature search to determine if the dopants that we predict are actually good dopants or dopable. And here are some results. So most of the time, you have some false positives and false negatives. So things that the model says are good dopants that are not, things that the model says that are not good dopants but are. But then most, of the things that were checked actually were accurate in terms of dopability. After doing this for cadmium chalcogenides, we actually extended to all zinc blend semiconductors. So zinc blend is the diamond structure, just with different A and B sometimes. So cadmium telluride was one of them, which was our starting. But when we also look at all the other 2,6s, all the other 3,5s, and the group 4, including diamond, which is very different from many of these other semiconductors. Even if you just look at pure cation, pure anion, so no mixings, you would, and if you consider the dopant or the impurity atom being everything in the periodic table other than the actinides, and you would have something like 12,000 possibilities. So that's much bigger sort of space in a sense, chemically very diverse. We focus on different defect sites, so we fix the defect sites to substitutions and interstitials, different interstitials. And then we do a number of DFT calculations and did the same exercise, correlating the input with the outputs. Here, we did not use unit cell DFT calculations. And it's seems like there are certain things that have very strong correlation as well, but nothing's overwhelming. So the way to deal with something like this, where you have a lot of inputs, a few outputs, and you don't know what combination of inputs actually matter, there's an approach called CISO, independent screening and sparsifying operator. That essentially is a kind of a trial and error approach in the sense that you have different inputs and you would combine them in different equations. So you have, maybe the ionic radii, maybe you have the electronegativity. So you maybe, square the ionic radii and divide it by electronegative. That doesn't make sense, but, different combinations, and the code doesn't care. You just combine all of them. And so from, 100 inputs, you can end up with 10,000 or more possible combinations. And then you use lasso, which is a sparsifying step, to pick out essentially the combinations that are useful. So that's what we did, and here are some of the results. I know that this looks worse, but I don't know, it's like a graphical thing. But the errors in the transition levels are pretty much in line with what we saw with just cadmium chalcogenides. So about 2.2 to 0.3 EV in charge transition levels, defect levels. And that's remarkable because this is all at chemistries. You know, you're talking about things with a band gap from like 1 to 5 EV. So this is a lot of different materials, and still a a unified or universal model actually does work. This was the online tool for predicting these ML levels that was included in the paper. So people can, and then all the data that I've talked about for the Perovskite project, for the defect project, are available on Materials Data Facility. So people can train their own models. People can use these models to make predictions. If you have new data, you can include it in your data and retrain a better model and so on. So just to conclude, we have, I think I lost the slide on the DFT accuracy. Oh gosh. DFT, just trust me in this. Okay, this is the top part is part of it. Before we did all of this stuff about defect, we actually checked how accurate DFT is in giving defect levels. And we came to the conclusion it's about 0.2 EV. PBE and HSE, so semi-local and hybrid functionals, actually perform quite similarly for the data that we can find in terms of defect levels. And the reason for that to be the case is that defect levels are total energy calculations. They are not eigenvalue evaluations, they are total energy differences. In any case, the machine learning models that are trained on DFT calculations are then used to predict formation energies and defect levels for water impurities in cadmium chalcogenides and later to all zinc band semiconductors. This is I mostly focus on the semiconductor part, but for anyone who's working on quantum materials, defect qubits is also a big field or growing field, rather, where people are interested in looking at these impurities in semiconductors and the defect levels and related properties. So this is very applicable to that as well. Okay, so how are we doing on time? I think, yeah, I have
Got about
another.
half an hour.
That's perfect. Okay, so this is a complete switching of gears. For many years, I did computation, and my group did computation. We sort of start with a structure, and sometimes we do a structure search using total energy, and then we do the properties. But increasingly, it has become clear to me that we need to know something about these real life structures. Because real life is not perfect. There's a lot of nanoscale variations, interfaces, surfaces, a lot of complexity that isn't in bulk perfect crystals that we need to determine. So one example, this was a gold nanocluster project we were interested in. We did a genetic algorithm search for lowest energy gold nanoclusters. This was 13 atoms. And it's insane because you see here, these are 12 different structures that have about 33 MeV per atom energy difference. So that's a very small difference. KT for room temperatures were 27 MeV. So all of these would be synthesized at the typical synthesis conditions, which is, maybe 1,000 degrees or something. And they are so different. The lowest energy structure is actually flat. So gold is actually unusual in that the lowest energy 13 atom cluster is flat. And then you have, very close in energy, you have another structure that's completely globular and symmetric, another structure that's flat. So there's a lot of structural variation where energetic minimization is not enough. Just knowing the energy is not enough. So, of course, our experimental colleague have been working hard on actually measuring and getting structural information on the nanoscale. With state-of-the-art machines, we have a synchrotron X-ray that has it's undergoing upgrade right now. The light just turned on after upgrading the accelerator. And this thing is huge, $1 billion project. It's intended to look at the structure of materials and molecules. Of course, in a more distributed way, we also have electron microscopes that are state of the art. I have visited Johns Hopkins. You guys have really amazing microscopes. And with all these machines, as well as atom probe, lasers, and all that, we get a variety of different data that tells us something about the atomic structure. But the process of trying to invert these characterization data is actually very, very tricky at times. That's what we have embarked on in the past 5 or 6 years. This whole inversion or characterization data using a combination of computational simulations, AI/ML, and of course the experimental data itself. So the first step is that we need to be able to simulate a realistic characterization signal. If a spectroscopy, a microscopy, I need to be able to simulate something that looks real. The reason is that if we cannot start with a structure and get a simulation of a measurement that is realistic, we will never know if we got the right structure. We'll never know if we got the right answer. So that was what we worked on a lot. Many former postdocs and students and collaborators worked on, for example, accurate core level spectra, so X-ray absorption or electron energy loss spectroscopy. The black lines are the experiment, and the red lines are the simulations. You can see a very high level of accuracy. Sometimes the simulation techniques are well developed. It's not the accuracy that's the problem, but so the realism. This is the case with electron microscopy, the multi-slice approach for electron microscopy simulations, as well as some acceleration that was developed by Colin Olfis, called PRISM. Those are good techniques. However, a lot of times the simulation is too clean. It doesn't look like a real electron microscopy image. So what we had to do was to include many different types of realistic noises and sort of aberration into the simulation so that they look realistic. The triumph of this moment came. This was the student former student Eric Schrenker, who's doing great now in industry. He was defending his thesis. On his committee was a well-known electron microscopist. He was showing some of these images, and the electron microscopist point to one of the images and said, you cannot take this part seriously because of such and such experimental artifacts. And so we were very happy because we were able to actually confuse an expert that to say that these images are real. So that's another part of the forward simulation. We need to make things that are simulate measurements or hypothetical measurements that are accurate but also realistic. Sometimes it's not the accuracy or the realism, but the computational cost. Such is the case for Raman spectroscopy. Raman spectroscopy is widely used to determine the structure of molecules and surfaces and bulk material. It's very painful for anyone who do DFT. They would know you have to do a photon a calculation, which is much more expensive already than typical ground state calculation. And then you have to perturb the structure phonon mode by phonon mode to calculate the Raman intensity. So one piece of work that we're working on with Nina Andreevich is to predict the Raman spectrum using a graph neural network called E3NN. So that allows us to accelerate these forward simulations and still get reasonable accuracy in many cases. So forward simulations, one part. And the second, which may be lesser discussed, is that we need able to determine a match. It might seem like a straightforward problem. If this is match or does it not match? But actually, it's not always. So in the case of microscopy images, in the Stone Ages, which was really just 8 years ago, maybe, we would literally look at an image and then put the image that we simulate on top of the experimental image in PowerPoint. And it was that ridiculous moment that I realized that we have to do something different. And so we developed this code called Ingrained, which is it has the goal of trying to match and determine the match of a simulated image and an experimental image. At first, we used electron microscopy as the sole purpose, but then it turns out that for scanning tunneling microscopy, that's also very useful. So now Ingrain works on both TEM and STM. And it's not just the matching, but also the alignment. Um, and in the case of interfaces, building the periodic interface samples, the width in the middle is the simulated image, and on the right are the structural models. So you can see that you get a structural model, and not just any structural model, but also with periodic boundary conditions, which is really important for subsequent electronic structure calculations. This is another collaboration with Paul Voiles that hasn't been published. This is an interface of two materials, and silicon and a metal that I don't know if I can tell you. This interface, it's messy, but Ingrained allows you to determine basically, the two crystalline part, and then we can work on the interface. So for scanning tunneling microscopy, which is sometimes also used to determine surface structures for electronics, there's additional complexity. Even if you have the same structure, because STM measures electronic density, basically charge density at different energies, even if you have the same structure, just putting in different simulation parameters will give you very different images. So Ingrain further allows for the optimization of those parameters. And in this particular case, we have this experimental data here, and Ingrain simulates with different parameters, and then try to determine where's the best alignment and match. So you can see, near the end of the optimization loop, it fits in really well with the experiment. So this was a fortunate sort of collaboration, I would say, for all of us, because our collaborator, Mark Hersom, was able to synthesize hydrogenated borylphane, which is single layer boron with hydrogen. But the structure was not exactly clear from just the STM. So using Ingrain DFT calculations and also additional validation experiments, including work functions and vibrational spectra, we're able to pin down the structure of borylphane as this hydrogen being on two very different sites, and kind of a crazy material. Okay, so we can determine a match. We can do simulations. There's not enough. We were still working on the inversion. Sometimes we are interested in extracting a piece of the structural information, maybe not the whole structure. So we would use pre-trained models. Again, this was a collaboration with Colonoffice. This is about 4D STEM. 4D STEM is 2D plus 2D. The electron beam raster in a 2D grid, and then at each point you get a 2D convergent beam electron diffraction pattern, or seabed pattern. So the seabed pattern, it's almost like the usual diffraction pattern, except that due to the stronger interaction of electron beam with material compared to, say, X-rays, you get multiple diffraction, and the disks are not like cleanly separated. They sometimes are overlapping. So one of them goal is to first turn these overlapping seabeds into Bragg dispositions, sort of a cleaner, typical diffraction pattern, which is essentially the Fourier transform of the electron density of the material. And from there, get the crystal structure, orientation, and strain. As in many of the other projects, we start with a lot of simulations, in this case, not DFT simulations, but electron microscopy simulations or 4D STEM simulations. We had to choose some materials, and what we ended up choosing was materials from different crystal structure prototypes, as well as from a wide range of atomic numbers. So then we calculated a large number of these seabed patterns, and then we had to work on a neural network architecture. because these are 2D images. Convolutional neural networks was the obvious thing to do. We tried sort of the simplest UNet, which is an architecture where you have smaller and smaller layers and then bigger and bigger. So that's where the U comes from. It was okay, but we figured that it wasn't working as well as we wanted it to. And one of the thoughts was that, okay, the seabed patterns is a reciprocal space object. We have like a real space symmetry and crystal structure to consider. What if we take a Fourier transform of the seabed? Now, of course, the Fourier transform of the seabed is not the real space, right? Because you lost the information, fully rationalized. When we put the Fourier transform as well as kept complex weights in the neural network, the results were very good compared to before. So here are some examples. These are the seabed patterns. And the one on top is a thinner material, so there's not a serious multiple scattering. And you can almost pick out where the Bragdon's positions are. I could tell you this is a regular diffraction pattern, and you'd be okay with that. And so traditional approaches, which is called correlation, does a reasonable job with this. But the Fourier complex UNet or FC UNet does a little better. But if you look at this one on the bottom, much thicker sample, it's basically impossible for any kind of human or rule-based approach to determine where the dots are. And in fact, correlation does a terrible job. But the FCUNet still does a reasonable job. Now you will note that these are 80%, not 100, and this is sort of a fact we have to contemplate and contend with when it comes to AI/ML. Especially when it comes to real life data like this. And that's the fact that like there's noise. These are statistical methods, and you will never get to 100%. So how close you can get is still, of course, subject to the individual problem, and maybe everyone can push the envelope a bit. But you will have to allow for the fact that there will be errors, and determine a strategy to deal with it. This is the test of this FCUNet model on realistic data. So this was silicon germanium layers because we can measure the composition of silicon and germanium, and we know how silicon germanium mixture behaves. We have a baseline expectation of the strain inside the material. And using the FCUNet and the 4D-STEM data, we can test how well the model works. So blue is correlation methods. You error in some places. UNet, which does somewhat better in predicting the strain. So just to summarize this part, this is an example of a pre-trained model that gives you a piece of the structural information or does a step in the structural inversion. This was for a 2D type of data, so we use a convolutional neural network, and the main innovation is putting in the Fourier transform of the seabed as well, and keeping complex weights, and which tend to improve the performance. Another example of the pre-trained model has to do with spectroscopy. We have for spectra data, which usually is a vector, right, of maybe 100 to 300 points. There's been a question, and several people have worked on it before, of how do you featureize? What do you take as input in, instead of just 100 to 300 numbers, is there a way to make the features more effective in a machine learning model? So I like this picture because it draws the face as a set of feature points. We don't do that anymore. Of course, we don't use handcrafted features for images, but in our amount approach and dimensional reduction approach, and train different models to see what works better. So what are the featureization approaches considered? One is, of course, the
Maria, you're breaking up a
Okay.
lot.
Sorry,
y-
what happened?
Zoom is saying your internet is unstable. Eh,
Oh, my internet.
Yeah, it keeps going red. Um,
I is that better now?
it oscillates between perfect and red. So I don't know. We lost your slides
Oh.
though.
Um, okay, but you can't hear me sometimes?
You
Hello?
break up sometimes, yes.
Oh, okay. Yeah, I am on my home internet already, which is the one that
It was
should
working
work
great until
best.
2 minutes ago.
Oh, I don't know what's going on. Okay, let's just, push on and um hope for the best. I'm almost done. Okay, where are we? We were here. Can you still see my share screen?
Yeah, we see it.
Okay, okay. Yeah, so different ways to featureize the spectrum, including one which was suggested to me by a collaborator called Mike Davis. It called cumulative distribution function, or just the integral of the spectrum. And I thought that was the craziest thing I've heard, because why would it make any difference? But there's apparently a whole field of measure theory that talk about cumulative distribution function, and so he convinced me to try it. Another approach that's often used with XPS is decomposing the spectrum into a number of peaks. And then finally, what's called continuous wavelets transform, which is an over complete representation that's sometimes used in XF's analysis. To jump over a long story, I am showing you the results of different featureization approaches, as well as different regression models. So we use ridge regression, gradient boost, random forest, and multi-layer perceptron. So many different machine learning models, sort of small, not deep networks or anything, because these are small data in a sense, and different featureization. So the dumb just means dummy. So like if you just randomly guess. So light colors are better. This is a lower error in bond length prediction. And then dark colors are worse. So you can see that several of the featureization approach, and especially the gradient boost and random forest regression, actually do a decent job. If you stop here, you would say that it doesn't matter that much how you featureize your data, and which of a couple different models you use, you can get good results. But I'm going to repeat this. We cannot stop there. We have to test the data on something outside, something slightly different, something from a different source. So we got experimental data, and this is from and I skipped over the source of the material because this is not battery talk. This is battery material called NMC, nickel manganese cobalt. We were looking at the nickel KH X-ray absorption data. And the key here is on the right, where blue is the ground truth nickel oxygen bond length. That's obtained by XFs, which is possible, just takes longer to do. And you can see the different greens are the different featureization approach. The dark dots are the original intensity. The stars are the cumulative distribution function, and then the other continuous wavelet transform and peaks. You can see that as a battery cycle, the material changes, the bond length increase and decrease because the lithium ion is moving in and out. And so that trend, the in and out trend, it's important. And you can see none of the other featureization approach have anything like it except the CDF. The CDF is actually systematically underestimating the bond length. We went and looked back, and that's very consistent with the fact that our DFT calculations had a lattice parameter that was slightly less than experimental lattice parameter. So the trend is well recovered, and the error is systematic due to the original training data. And this is not a one-off, it's not a fluke. We have trained and tested on other types of data. So this was come from a completely different source with a collaborator at Berkeley Lab. the soft X-ray parts, and it's the same story where CDF actually gives much more reasonable predictions or inference compared to the other featurization approach. We have worked on, and I didn't put the slide on the reason, but one of the key reasons is that in realistic spectra, the actual edge position is not always very well determined. The calibration conventions from different synchrotrons can be different. In simulations, it's very difficult to get the exact edge right. So what happens is that CDF is much less sensitive to the absolute edge position compared to the original spectrum. That allows the model to pick out, sort of focus on the shape of the spectrum rather than the actual position. And this is going to be a problem for many, many different characterization techniques, spectroscopic characterization, or even scattering, because sometimes there's a slight difference in lattice parameters, so your XRD peaks will be off. Sometimes there might be temperature effect, so your Raman peaks will be slightly off, and so on. So, thinking deeply about how you featurize your data and testing for realistic noises and errors, it's important. Can you still hear me? Is everything okay?
It's working much better again. It's working much better again.
Okay. Okay, thank you. So to push this further, we're looking at how to determine these tiny defects in the battery material or other materials at interfaces and so on. So this is a tricky problem. It's very hard to do individual measurements of defects. You can only get an optical signal a lot of times, so that's a bulk signal. But one approach to do it is with electron energy loss spectroscopy, not directly just measuring the yields, because it cannot tell you very well where the defects are, but by measuring different edges in the yields and training an ML model to pick out what are the signatures of defects. So this was one example from Haley Jia, who's just graduated from Johns Hopkins, a student who worked with me remotely. So she showed that manganese and nickel and cobalt, if you look at the L edges, which is the transition metal L edge accessible with yields, you have some accuracy. And she started with 0.5, which was slightly illegal, but as long as you notice that. Manganese, nickel, and cobalt are somewhat okay in predicting an oxygen vacancy. And oxygen spectra nearby also tells you. But if you include all of that information, all the edges, it gives you a much higher likelihood of getting the correct answer. Just to summarize, this is a second case of a pre-trained model that extracts structural information, maybe not the whole structure. But some of the key things to take away is that we need to think deeply about the input, how to featurize the input in these machine learning models, and also how to combine different sources of information, which often becomes much more effective in giving you your answer. And last step in this inversion is our sort of pride and joy fantastics, which stands for fully automated nanoscale atomistic structure from theory and experiment. One of the previous student question was about fully automation. We are working towards that. This isn't about controlling the machine per se, but about interpreting the characterization data that comes out. The central idea is that the same underlying atomistic structure is responsible for a lot of different measurements: X-ray diffraction, electron energy loss, Raman. So by combining different sources of information, we can pin down that structure a lot better. So fantastic work on sort of two loops in a sense. One of the loop is a sanity check. Energetic information either from DFT or interatomic potentials, so both classical and ML potentials, give us some information on what arrangement of atoms are not crazy. If you ever done a fitting with experimental data alone, and we did, you will see that sometimes you get structures that are completely crazy from an energetic point of view, but it matches the experimental data. So the two loops sort of work together to both narrow the number of possibilities and get it more realistic. But of course, those two live on this generative loop, which create new possibilities. Of course, we have been, computational material scientists have been working on structure search for many, many years. Monte Carlo genetic algorithm based on hopping, those are the more conventional structural creation algorithm, structure search algorithms. But we're also working on graph neural network based generative models, which we're hoping to increase the sort of understanding as well as the speed of the search. But of course, one challenge is that these generative models you saw in the last talk require a very large data set. And in the case of being able to accelerate a test, that works against you. So this is an example of Fantastics in action. The lower right is the original STEM image. This is an interface, grain boundary, in fact, inside cadmium telluride solar cell. The lower left is an automated simulation and match. So a score is returned for every simulation, every structure. The score of the energy and the score of the image match are combined to show you here, but we actually perform a multi-objective search so that those are independent factors. After a while, we went from exploration to exploitation just to change fewer of the atoms, but try to push down the fit. And in the end, you get a structure that has an interface that is not conventional. There have been a lot of modeling on conventional grain boundary structures, which are, very clean. You see the dislocation core, but in this case, it's not very clean. And this is sort of the point we're trying to make, that real systems can be messy. Despite your perfect crystal structure, you can have messy interfaces, surfaces, defects and all that stuff, and being able to combine experimental and computational information, theoretical information will help you get there. This is another example. This was a really cute tellurium layer in the middle of cadmium telluride. We nicknamed it tellurium snake for a while. So again, work with Robert Klee. This structure was the one that we squint and look at in PowerPoint, when we made it. This was 2018 also. And with Fantastics, this took the time from months to days. We fed it in the input information, 100 models in, all automated. It found the structure that we found before. There are other applications, not just to microscopy. We have done pair distribution function fitting for Fantastics. Again, comparing to a previous attempt that a collaborator had done, it sped up the process and made a slightly better fit. And we were extending this to X-ray absorption with molecular structure. One of our future plan would be X-ray absorption for crystal structures as well as X-ray diffraction. Most of the time when you do XRD, you can find the pattern in some kind of database. But just in case, this is called in the XRD world ab initio structure search, finding a new finding material that hasn't been seen before or not in your database. Fantastics is also able to do that, and even with sort of messy experimental data, not very clean ones. This is our program we have been working on. So what's the big deal? For people who do computation, it may not be necessary to emphasize, but I like to just put it in for completeness. When you have a realistic structure, you can do materials design. So we have this paper where we have, this is a cleanish dislocation core structure, but even with messy structure, you can do the same thing. You have a defect in the material. It causes mid-gap states that cause recombination and lower your lifetime and therefore device performance. How do you fix it? So we can actually include grain boundary passivants, different atoms, just take different atoms in your structural model, do the calculation, look at the electronic density of states, and see what decreases the mid-gap states most. And this is sort of a way of doing materials design. Of course, we're interested in situ interpretation. With upgraded synchrotrons everywhere, we're getting a huge amount of data in a very short amount of time. So cutting out the human and making the data interpretation more automated allows us to, get the results much sooner. And then also get some fundamental understanding. This was another example where we look at interface in a battery and how it contributes towards oxygen stability and degradation. So the problem there was that I can build models of interfaces, thousands of them with a click of a button, but which one is real? By really focusing on the realistic ones that have been observed in the material, it allows us to really focus our effort and get sort of more confidence in the fact that our models are and interpretation are reasonable. So all this work has led us to a hunger for experimental data. For those of us who grew up in the academic sense, doing or moving towards the high throughput computation era, the fact that experimental data it's much harder to get a lot of and standardize it's a pain point. So we have been working on characterization data infrastructure together with some other nano centers. We are also in parallel working on gathering microscopy and spectroscopy data from literature. So now this looks like the obvious thing to do with the LLMs, but when we started this quite a while ago, from the beginning, it was not really sort of sensible almost. It was thought of a bit crazy. There was a lot of steps involved in extracting microscopy and spectroscopy images from literature, and steps that we did not expect were so important. It turns out that people put figures in papers in random ways, or not random, but very many different ways. And being able to separate a figure into the part A, B, C, and being able to figure out which one is a microscopy image, which one is a plot, which one is a drawing, was actually a significant step. So we did all that, and this code is called Exclaim. As you can see, we have a penchant for very long acronyms. But Exclaim, it's available, and we've now infused LLM capability to it, so it's much better. It separates an image, it classifies it with a different neural network, and it extracts description of the figures from caption and text. So the last part was made much better with large language models. And further, we are digitizing the plots as well, so we can get a microscopy database or spectroscopy database rather. With image and text together, you can do a lot of really fun things like multimodal training, and look at the embeddings, look at similarities. And Katerina Risa, who's a new staff scientist at Argonne, who used to be my joint postdoc, has been doing great work on this. Like I mentioned, digitizing spectra. And the way Katerina and her collaborator, Henry and Jay, have been using this is to really infuse it with robotic synthesis capability to make new material. So if you just go to lab and make something new, where do you start? That's all based on your intuition and understanding. What we're trying to do is to incorporate community wisdom, so to speak. So Katerina took molecular information from papers. She digitized the optical absorption spectrum, and that's all towards making new electrochromic polymers. All this data from literature was used to train machine learning models, and then the output of that model informs its autonomous synthesis. So we can do this in a loop. They do a few steps in this loop and sort of drive towards the color electrochromic polymer that they wanted. So with that, I like to end. Our GitHub is called Materialize. It's a play on the word materialize, like make happen, but also materialize. It turns out to be a band as well. These are a few snippets of the work we've talked about in terms of inverting characterization data, in case anyone is interested. I like to acknowledge funding from the Department of Energy primarily, and also the NSF MERSHAC, and a lot of computer resources, both at Argonne as well as in NERSC, which is at Berkeley. We are a user facility. That means anyone interested in any of the things I talked about, or just computer time or any software that we mentioned, is welcome to contact me, and I will get you set up with a user proposal for free access as long as you're doing open scientific research. With that, I'd like to thank you for your attention and love to take any questions. And I apologize for the connection instability.
Thank you for the wonderful talk.
I went over, sorry.
We do have time for some questions, Maria.
Oh, thank you. Actually, the fantastic like it kind of answers my question that I asked earlier. But I have something to ask furthermore. Like, so I see that you have trained the FCUNet algorithm using simulated images, right? So
Yeah.
and my question is why? Why don't you just directly use the experimental images? So in that case, you can directly pipeline the algorithm to the SGM STEM machine or something like that. So why you have to go for a simulated image, then you train that? Because in case if I come up with a new fresh image, then I don't know if the FCNet will able to make predictions.
Yeah, that's a great question. And this is a question we asked all the time. So first of all, I'd like to clarify that the FCUNet is one model on all chemistries, all systems. So it's not like you have to train a new model for every new types of material. It's really one model for everything in the periodic table. So it's supposed to be universal. And the reason we cannot do this with experimental data is the simple invisibility of getting all these samples and measuring them. We were, in the end, I think we had 200,000 4D SEM image that was used for training. And that was not something that you can do like experimentally because the samples involve, thousands of different materials with different crystal structure prototypes, different orientations, different sample thickness. So, all of that are not like within the range of feasibility. This is the same thing for our other pre-trained model projects, which had to do, say, with X-ray absorption spectra. The question was asked, why can't we use experimental data to do training? And the answer is you cannot control the composition of the experimental sample in the way that we can control the simulations. You cannot actually do, we had 3,000 X-ray absorption spectral measurements. You cannot, basically, there's no synchrotron that will give you beam time to do 3,000, even if you could make the sample. So I think this is a thing that we have to come to terms with in many cases. Our models have to rely on simulations. And therefore, it is very important for the simulations to do a really good job in reproducing the experiment. And it is very important to test our machine learning models on experimental data subsequently.
Hi, Maria. Thanks for the talk. I kind of have a specific question on the ingrained. So I'm working on some stuff where I'm trying to map out structure on TEM images, kind of like either going the route of simulating a 4D stem by taking local FFTs, or and trying to decide if I should be training a model to like a neural network to identify those real space, or going from like a database of simulated crystal structures, and instead of like training a model, just fitting kind of thing. And so I was kind of curious how you guys determine when more of a fitting approach is appropriate versus a ML or neural network approach.
Yeah, so the way I think of it is like you have pre-trained model or you have iterative search. If you have something that's, it can be reasonably enumerated, like inorganic crystal structures, perfect inorganic crystal structures, then sort of a pre-trained model makes sense. Because there's been a lot of XRD models where people try to identify the structure with XRD with pre-trained models, because there's a discrete set, and it may be 200,000 or 300,000 different crystal structures, but it's sort of countable and enumerable. The time when we have to do iterative search, which is what you call fitting, I think, is when you have the space is big enough that you don't think a enumeration approach can work. So this is for things like interfacial structure, nanostructure, where you just can't count the number of ways it can be different, because it's not just vacancy or I don't know if you're familiar with cluster expansion. Cluster expansion works when it's on site, when you can count, is the atoms there or not there, species A, species B. But for interfacial structure, you don't have that, as you saw in some of the examples I gave. It is not, there are no clean lattice sites. And you cannot list all the ways the atoms can be, positioned at this interface. So for something like that, I think an iterative approach or fitting approach where you come up with new possibilities continuously may be more fruitful.
Okay. Thank you. We have time for one last quick question, if anyone has a quick question. Okay. Well, thank you, Maria, for the
Thanks.
wonderful talk and for doing this. So
Thank you.